Alright, dear children of class 11 science, so we do now the topic that is very important, from where we write the expression of amplitude, frequency, time period, velocity, acceleration of the motion occurred by the particles under simple harmonic motion. And this can be represented as a projection of uniform circular motion. That's why your topic name is simple harmonic motion as a projection of uniform circular motion. Now uniform circular motion means the motion occurred by the particle in a circular path. The simple harmonic motion, as you have learned in details already, is the simplest form of oscillatory motion. The simplest form of what? Oscillatory motion. Because oscillatory motion are the periodic motion. So one of the type of oscillatory motion or periodic motion is the simple harmonic motion. That's why let me just add a point. Simple harmonic motion is one of the simplest form of what motion? Oscillatory motion. Now for this simple harmonic motion to express as a projection of uniform circular motion, we can consider a particle. We can consider a particle moving in a circle. Moving in a what? Circle with a certain radius. And I take that radius is what? Say A. So I write down A be the what? A be the radius. This is the radius of a what? Particle. The radius of circle, sorry. The radius of what? Circle. In which the particle revolves. And this particle will move with a constant angular velocity. What velocity? Constant angular velocity. So I write on it omega, this is called omega, be the what? Constant, this is a constant, what velocity? Angular velocity. Because as long as the circular motion is concerned, we can measure the velocity called what velocity? Angular velocity. But remember this, when the body moves in the circular path, the velocity at any point on particle can be expressed by a linear velocity also. What velocity also? Linear velocity. So I write on that linear velocity is B. So let B be the what? Linear velocity. And children, you have learned in one of the chapter called linear circular motion, uniform circular motion, the relation between angular velocity and what? Linear velocity. Now in order to express the motion of simple harmonic particle in simple harmonic motion as a projection of uniform circular motion, so let me take this circle, and let me draw the line. One is the vertical lines, another in the horizontal line. And these two lines intersect at this point, and we know this is the center of the circle. So let me mark the center of the circle as O. Now let me represent this line by a name x dash. Or you can write this way, x dash x dash. Similarly, there is a vertical line which I have drawn, and this line let me give the name as y dash. Now these two lines intersect at this point. So definitely the distance from this point to this end, where this is also called the circumference of circle, is equal to the radius. Is equal to the what? Radius. But when a particle is in a circular motion, uniform circular motion, at any instant of time, the particle may acquire any position. And let me just take the particle is at this position. For example, if the particle is at this position, and this position I consider as P. So at any instant of time, the particle is at position what? P. So P is the position of the particle at any instant of time on a circle. So what I do, from this O, the distance from O to P is marked by letter A, that is equal to the radius of the circle. That means particle when it's at P with respect to center, OP, the distance OP equals to A, and this A is nothing but the radius equals to the radius of a what? Circle. The radius of a what? Circle. Now from this point P, I drop a perpendicular line on YOY line, on vertical line. So I draw the perpendicular line this way. So this perpendicular line will meet somewhere at this point, and let me mark this point as say M. So I am marking this point as what? M. Similarly, the same perpendicular line can be drawn on this line also, and this line x, x dash also, and the line will meet somewhere at this point. Let me mark this point as N. Okay, let me mark this point as what? N. So with the vertical line, okay, the particle acquire a displacement, okay, and this displacement is given by y. So y is the displacement particle on this axis. Similarly, the particle acquire a displacement along x-axis, and that is given by x, small letter x. Small letter what? X. So in this particular diagram, if you see this M is called the projection of particle P on the diameter what? Y dash. Because this is the diameter of circle. This distance and distance are the diameter of circle. So to understand that where the particle is projected, okay, the projection of particle on this diameter is simply given by the point called M. So the perpendicular line which I have dropped out here on y dash represent the projection of particle on the which line? On the diameter what? Y dash. So as the particle moves from x to y, see, particle moves from x to y. That means, let me take the case the particle is moving this way. The particle is moving this manner. So this is usually anti-clockwise. Okay. So when the particle moves from x to y, okay, along the circle, okay, the projection M moves from O to what? The projection M moves from O to what? Y. The projection M moves from what? O to what? Y. Similarly, when the particle moves from y to what? X dash, means this side. When the particle moves from y to what? X dash, along the circle, the projection M moves from y to what? O. That means projection moves from y to what? O. And when the particle moves from x dash to y dash, the projection M, okay, the projection M moves from what? O to what? O to what? Y dash. O to y dash. That means whatever position acquired by the particle with respect to O is actually represent the projection of the particle with respect to the center point, and that center point is what? O. Similarly, when the particle moves from y dash to x, then the projection M, okay, moves from y dash to what? O. Okay, so this is the way the particle may move in the circular path, okay, acquire a motion, and this type of motion acquired by a particle is related to what? A simple harmonic motion. That's why simple harmonic motion is the projection of uniform circular motion upon the what? Diameter of the what? Circle. On the what? Diameter what? Circle. But we consider that the particle in a circular path moves with a reference line on a circle, and this reference line we consider as x dash. So we consider this line is the reference line in a circle to express what? A motion called simple harmonic motion. That's why under this projection of simple harmonic motion in a uniform circular motion, when the particle oscillation is from O to Y, and from Y to O, and from O to Y dash, and Y dash to O, makes one oscillation. It makes what? One oscillation. And this oscillation is also called one vibration. One complete oscillation also called what? One vibration. So under this condition, simple harmonic motion may be defined as the motion of the projection of particle. The motion of the what? Projection of particle on any diameter of a what? Circle. Any diameter of a circle. Okay. So like in this case, we can see the projection of particle on the projection of particle, okay, on a diameter y dash, okay, with reference to the reference line, that is what? X dash. That means we are taking the case where the particle is starting from this point and moving in this manner, in an anti-clockwise manner. But with respect to this reference line, when the particle start having a motion, a uniform circular motion, at every position the particle acquire a position. Okay, and that position of the particle with respect to a center point is expressed by the projection. And with this projection, the particle have a to and fro motion. Okay, we consider like it has an oscillatory motion. Okay, so under this consideration, we can measure the displacement equation of simple harmonic motion. Now we measure the what? First part, that is displacement equation. So the topic that we are going to do now is, with respect to this same topic, is displacement equation. Okay, displacement equation of simple harmonic motion. Now, displacement equation of simple harmonic motion, okay, can be done from this figure only. So we have already drawn the diagram out here. Okay, now with this figure, if you see, the displacement is the distance traveled by a body. So displacement is the distance traveled by a body, okay, having simple harmonic motion from the what position? Mean position. From the what position? Mean position. Okay, now out here, I consider the particle starting from this reference line. Now I consider this reference line is act as a what? Mean position. So once particle move from this reference line or from mean position, the particles, okay, acquire a position, and that position you can already see at P. When the particle is reached at P from this reference line called mean position, okay, at any instant of time, then there is a displacement of the particle with respect to this line, and this displacement is called angular displacement. This displacement is called angular displacement, and we mark this angular displacement by theta. So out here you can see theta is the what displacement? Angular displacement. Okay, this is the angular displacement of a particle. Okay, particle. Now this angular displacement takes place by a particle at any instant of time, at any say instant of time, and that time I consider as t. So if theta is the angular displacement, then theta is also written as omega into t. Angular displacement is equals angular velocity into time. So that means this theta equals to omega into t. Okay. Now this is the angular displacement of the particle. But with respect to this diameter, OM, if you see OM equals to nothing, the OM is nothing but the displacement. You can see this is the displacement of projection of particle at that instant of time. So that displacement is marked by letter y. And this is along y-axis, this along x-axis. So this displacement along y-axis is equals to the displacement of projection executing simple harmonic motion at that instant of time. So this is the displacement. And we call this displacement also as linear displacement. We call this also as linear displacement. So displacement of projection. Let me write the word displacement of projection executing what? Executing simple harmonic motion at the time which I consider is what? T. Okay. Now from this diagram, if you see this line which I have drawn, that is called OP equals to A. OP equals to A. This is Y. Okay. OP equals to A and this is Y. Now what I do now, I measure the distance. Okay. I express this distance, displacement, that is OM. Okay. In terms of this this particular the radius, that is called A. But this A is also the amplitude. So outer A is also equivalent to the amplitude of the displacement. Amplitude of the motion, the simple harmonic motion, acquired by the what? Particle. And you know, under simple harmonic motion, the amplitude must remain what? Constant. So if the particle is at P, amplitude equals to the radius of the what? Circle. And the particle is another position, then the amplitude remain what? Constant. Now student, I follow a right angle triangle that you can see in the figure, that is O, you can see OPM, or we can write OMP. Okay, let me write OMP. This is OMP. Because OMP means this angle is 90 degree. So I am taking the same right angle triangle out here. OMP. OMP. So this is a right angle triangle. Okay. Now if this is a right angle triangle, OMP, then this angle is theta. Then this angle is also how much? Theta. So this angle is also theta. Because the two lines are parallel and this line acts as a transversal. You have learned in geometry. Alternate angles are what? Equal. So this is in OMP, this angle is 90 degree, this angle is theta. Okay, and this side equals to A. But in a right angle triangle, this is your base, this is your perpendicular, you have learned, and this is your what? Hypotenuse. Okay, now to express this perpendicular, the displacement, this is your displacement, y, in terms of the known quantity that is called hypotenuse. We follow what? Sine. Because sine theta means, some people have, sine theta means perpendicular by hypotenuse. Okay, and what is the perpendicular in the diagram? OM. Children, look at it. OM is your perpendicular. And what is the hypotenuse? OP. OP is your hypotenuse. So sin theta equals to OM by OP. So if I cross multiply, then OM equals to OP what theta? Sin theta. Now see, what is OP out here? A. A is the radius of the circle, but this also equals to amplitude of the simple harmonic motion, equals to A sin theta, which means OM is Y, so Y equals to A sin theta. So children, look at the expression, Y equals to A sin theta. Now if Y equals to A sin theta, then I write the same Y equals to A sin theta means what? Omega t. See, we have done it earlier. Theta means omega t. So this is the displacement of the particle at any time under a simple harmonic motion. That means Y equals to A sin theta. Okay, so this is the expression of displacement equation under simple harmonic motion. Now with this displacement equation, we can even calculate the amplitude, we can measure the velocity, we measure the acceleration, okay, we can measure the force, and even we measure the time period executed by the simple harmonic motion. And that quantities that we are going to measure we'll do in the next YouTube video. Means we do continue with the same topic in the next YouTube video.